Similar is also here. I mean, the torsion is a tensor, but it's sufficiently homogeneous. And you can just make a geometrical proof like you do it for Riemannian space. You can make a proof for Riemann-Cartan space that this elevator is possible. So this is very similar to each other.
But the physical content are different.
Yes, because here you have a normal, a natural frame, and here you have an arbitrary frame.
So here you can always choose in the Einstein-Cartan theory, you can always choose and also for an harmonic frame to make the torsion. I mean to make this gamma zero.
Yes.
But
it doesn't mean that the torsion is zero, because the torsion depends not only on gamma but also on the curl of
right.
So gamma can be put to zero, but it's not the torsion.
In principle, based on the Einstein laboratory and also the principle based on the Kibble laboratory, there are two different different type of principle.
Yes.
This has to be tested by experiment. Okay. I just pointed out to students how.
No. I mean, you also pointed out to me. That's good that you remind me that there are two different.
You knew that very thoroughly, but I just point out to. So they have different physical content which need to be tested by experiment. Okay. But of course, to test experiment, you always need a model to see what is the level you need for the anharmonicity.
Yes. This is true. I mean, I have no way. I didn't develop experiments how one can distinguish one from the other. But I think okay. That's all I have to say to that. I think if one just extends Einstein's ideas to which he applied to mass points to Dirac electrons and just rethings and redoes things as he, so probably he would have done it this way if he had known particles with spin at the time. 1915, spin was not yet discovered. Spin was discovered 1927, I believe.
Yeah, formally it's around 1925.
Yes.
With the atomic spectrum.
Yes.
And later by Stern-Gerlach experiment, which is much more
okay.
recognized.
So we agree that we can have now the last line which I want to fill in. Is really just the field equations, which I think can you read it if I write it here, or should I put it? Well, I can also write it here. So I put it here. There is one line missing. This is Einstein's lab, and this is Kibble's lab. There is one line missing, and these are, of course, the field equations. The Einstein field equation, if you know you have a Riemannian geometry, you just take the Riemann scalar, the contraction of the Riemann tensor, so twice the contraction is the Riemann, or the Ricci scalar is often called, and you have a variation of principle with this Ricci scalar. And what you can do here is the simplest thing is to do the same. You have a Riemann-Cartan space with a corresponding Riemann-Cartan curvature tensor, and you contract it twice, and you get a curvature scalar. And then you develop the field equations, and these are then the analogs of the Einstein equation. So in the case of the Einstein laboratory, if you do what I said, then you get the Ricci tensor as field equation, the Ricci tensor minus 1/2, how did I write it? Well, simply with the trace of the Ricci tensor. is proportional to the energy momentum T. And in Kibble, you get, and this Ricci tensor for Riemannian spaces is symmetric. So I have here a Kibble for Kibble and the Sciama-Kibble field equation. I call it Kibble's laboratory because Kibble discussed it really in this way. Sciama had a little bit a different conception. He was earlier than Kibble. What he first did was to take general relativity for granted, and then he gauged the Lorentz rotations on top of general relativity. Whereas Kibble started with special relativity and gauged the translation of the Lorentz rotation at the same time and immediately arrived at the Riemann-Cartan space-time. Whereas Sciama, who was earlier, first took general relativity, formulated it in tetrads, frames, and then he gauged the Lorentz rotations, and then he arrived at the field equation. But the laboratory which is analogous to what Einstein did is that what Kibble did, a bit later than the Sciama. So, and the field equations then look very similar. We have here Ricci, but now with respect to the Gravitation scale or not. Ricci minus 1/2. I'm going to derive these equations in the second part of the lecture. Proportional to energy momentum, I should have called this it's small t. It's a symmetric energy momentum tensor. It's the Hilbert energy momentum tensor, which one gets by variation with respect to metric. And here we get the canonical energy momentum tensor T. And you get a second field equation, which is torsion plus 2 times trace of torsion symbolically is proportional to speed. And here is, well, the gravitational constant, the gravitational constant, the gravitational constant. And these equations we will. So this is both recipes, and you see that in a natural way, because also in the Riemann-Cartan space we have a Riemann-Cartan curvature scalar, and we can vary this curvature scalar with respect to the co-frame and the connection, and then we get two field equations. If you vary with respect to the co-frame, we get the first Einstein type of field equation. But this Ricci tensor is no longer symmetric. Like here, it's asymmetric, it has an anti-symmetric piece, and we get the second equation, which is relates torsion to the spin of the electric field. I think this is now an hour. Should we make now a break? How long? 5 or 10 minutes?
Maybe we should go back at 45.
45. And if you have questions, I don't erase it so far, so come and